Hello everyone, this is Hamada Risk. Today I'm going to share with you Gain Without Pain, enabling fingerprinting-based indoor localization using tracking scanners. This is a joint work with Professor Hirizumi Yamaguchi and Professor Mustafa Youssef and Professor Tiro Higashino. As people spend most of their time indoors, recent years have witnessed an ever-growing demand for accurate, ubiquitous, and easy-to-deploy indoor positioning systems in many applications, including location tracking, navigation in big malls, crowd detection, and even emergency services. The criteria for the aimed localization system is to be accurate enough for indoor setting, ubiquitous depending on ubiquitous technology like Wi-Fi, easy to deploy and maintain in terms of the data collection effort and time, and finally comes with low cost, and usually this cost is due to the infrastructure setup or maintenance. Towards making these objectives possible, Wi-Fi is widely adopted due to its availability indoors with high density of covering access points. And to achieve the intended accuracy level, fingerprint-based approach has been shown to be capable of providing accurate and fine-grained positioning. Actually, fingerprinting works in two phases, offline and online. During the offline phase, the received signal strengths from the access points installed in the area of interest are recorded by a cell phone carried by the site surveyor. This is done at specific reference points, the blue circles in this figure, and the site surveyor has to remain at the exact points over a relatively long time and tags these recorded data manually through the use of data collection application. So the output of this process is a fingerprint database, which is then used to train a localization model for estimating the user location in the online phase. On the other hand, fingerprinting has several problems, including the excessive deployment and maintenance cost. It requires the user to be stationary at the reference point, which is not easy process. And the scalability is a problem, especially in large environments. And the change in the environment necessitates the recollection of a new up-to-date fingerprints. And to tackle these problems, several techniques have been proposed, including the use of crowdsourcing robots, which don't account for the effect of human body, and they also require a calibration process. Interpolation techniques have recently proposed, but still require data collection process in order to use the collected data to generate artificial data, which may not reflect the typical signal patterns. Finally, computer vision solutions are also proposed to tackle these problems, but they raise privacy concerns and they require a complex calibration process. The basic idea is to opportunistically leverage transportable laser range scanners in a user-transparent way to tag Wi-Fi scans collected during the normal movement of building users without human intervention. LRS is a device that uses the laser beam to detect surrounding objects in large indoor environments, such as mall and museum. It obtains accurate distance at each angle and now becomes less expensive. We designed a battery-operated version, this one, with a place-and-play features using Raspberry Pi 3 and LTE module. Therefore, the setup overhead cost of the LRS-based tracking system is negligible, which includes placing the LRS in a specific location and marking its location on the map. Although one LRS can cover as large as 30 square meter area, the whole area of interest can be covered incrementally using a single LRS. The main challenge here is that LRS traces or labels are anonymous, such that the users who created these traces cannot be identified. Therefore, LRS-based labels cannot directly be used to tag Wi-Fi scans collected by those users. Secondly, handling the temporal changes of Wi-Fi signals, which negatively affect the Wi-Fi localization performance. These changes may occur in short or long duration, and it affects the quality of the fingerprint database and the model which is built on this database. This figure shows two distribution of an arbitrary access point at the same location in two different months, July and November, which depicts how the distribution changes over time. So our contribution is LiPhi, an accurate system for enabling fingerprinting-based indoor localization systems without the associated data collection overhead using LRSs. LiPhi also introduces a technique that leverages crowdsourced Wi-Fi scans to roughly estimate the user trace and match it to LRS-derived ones to identify and tag the Wi-Fi scans. It also incorporates modules to build and maintain a robust localization model. And finally, we deployed LiPhi in two realistic indoor environments. This is our agenda for today, and we will start with the details of LiPhi system. LiPhi consists of two stages, offline stage and online stage, with several modules, and mainly we have LRS trace estimator module, which estimates anonymous traces using LRS, and we have Wi-Fi trace estimator module, which estimates the coarse-grained user traces using Wi-Fi signals, and the trace matcher matches the resulted traces to refine the annotation of the Wi-Fi scan using the labels of the matched LRS-derived trace. And we obtain a fingerprinting database, which is then used to train a localization model to be used in the online stage. LRS-based trace estimator estimate the user trace using 2D LRS unit, and the user location is estimated as a center of arc-shaped group of points, and the user trace is formed by connecting subsequent location estimates, as can be shown here from the video below. So the output of this module is an accurate trace, but anonymous, so we don't know which user created which trace. Wi-Fi-based trace estimator. The basic idea here is that the measured RSS from different access points can ideally represent the distance between the ABs and the device. In other words, the stronger the RSS received from an access point, the closer the device should be to this access point. For example, this point is closer to access point B rather than access point A. So the RSS from access point B is expected to be stronger than the received from access point A. Therefore, LiPhi generates rules represent the expected RSS relations between every possible pair of access points at each location. And these rules characterize these locations. And to enable the effective calculation of these expected rules, LiPhi discretizes the area by creating a grid which is virtually superimposed on the layout of the area of interest. Wi-Fi scan annotator. It estimates the user's most probable location based on the received Wi-Fi scan. Assume that the user at unknown location receives a Wi-Fi scan like this one. LiPhi then generates the corresponding rules, which is matched to the expected rules at each reference point in the area of interest. Then the center of mass of the high-scored matched points is considered the user location. Trace matcher. Here, the Wi-Fi trace is matched to the most similar LRS-derived trace, and the coarse-grained labels of Wi-Fi scans are refined using their corresponding LRS-derived ones. The output of this stage is the fingerprint database of labeled Wi-Fi scans. These scans are fed to the localization model builder to build a localization model of a fully connected neural network. The output of this network consists of two neurons corresponding to the spatial coordinates X and Y. And to increase the robustness against overfitting and fluctuation of access point, LiPhi randomly switch off some of the access points in the training, generating new synthetic samples like these two samples. This has the effect of making the training process noisy, forcing the model to learn and generalize from incomplete input vectors. Additionally, device heterogeneity and temporal variations usually shift the signal magnitude with some variance. Therefore, we emulate this behavior by adding wide Gaussian noise to the original input vector, generating noisy vector, which smooths the boundaries of the underlying distribution, enhancing the generalization ability of the deep model. During the online phase, the user is tracked in continuous space. This is done by feeding the RSS scan to the trained model and estimate the user location. Additionally, the model updater can be used to update the fingerprint database and, if needed, to fine-tune the trained model. The evaluation. We deployed our system in two different environments of different sizes and different densities of LRS, and the testing points were collected using traditional fingerprinting. Several Android phones were used for data collection in training and testing. The effect of different parameters. The figure showed the effect of changing the virtual grid spacing on the overall accuracy. And as expected, a smaller spacing between reference points yields high localization accuracy with negligible delay in the calculation in the offline phase without affecting the real-time response on the system. 1 meter spacing is enough to maintain high accuracy of LiPhi. This figure shows how the system performs by changing the number of reference access points whose locations are known and show with as low as 5 reference points that there is some drop in the accuracy of the Wi-Fi location estimator. However, the overall performance of LiPhi maintains steady with an error around 1 meter. And this high accuracy with a relatively lower number of access points is due to the location resetting using the accurate LRS trace estimator and also the use data augmentation techniques that help the model to maintain its accuracy even with low number of access points. Here we evaluate how the system would perform in the two different test beds. The floor test bed is larger with many rooms, therefore it requires a wider coverage of LRSs, while the office is smaller and open area without inner walls. In the floor test bed, 6 LRSs are leveraged to cover the whole area of interest of 12 rooms incrementally, and the office test bed has 4 LRSs covering the entire area of interest. LiPhi obtains better performance in the floor test bed as compared to the office test bed. This can be justified due to two reasons. The first one is the number of the considered ABs in the floor test bed is more, which favors its performance as the model learns more information. Secondly, Wi-Fi signatures are more location discriminative in the floor test bed due to the presence of walls and the richer multibus environment. For evaluation purpose, we compare the accuracy of LiPhi to two state-of-the-art fingerprinting and crowdsourcing-based techniques called WiDeep and hybrid lock. WiDeep is traditional fingerprinting technique which builds a denoising autoencoder for localization. Hybrid lock is a probabilistic Wi-Fi-based localization technique that automatically constructs the fingerprint database using label obtained from 10 BLE devices. For fair comparison, all techniques are deployed in the same environment. The figures show the accuracy of the three systems when tested with a fresh fingerprint and 4 months later. In the first figure, LiPhi and WiDeep, the blue curve and the purple curve have superior and equal performance even though WiDeep is trained with manual fingerprinted data, while LiPhi is trained with automatically constructed fingerprints. The second figure shows how all systems would perform when tested 4 months later. LiPhi outperforms WiDeep and hybrid lock because of the data augmentation methods in the training data, which gives LiPhi greater flexibility and generalization ability. Despite the high overhead spent to collect data for WiDeep as a traditional fingerprinting technique, its accuracy cannot be maintained without redoing the arduous calibration process. In conclusion, we presented how LiPhi automatically constructs a fingerprinted database for indoor localization using LRSs. We also presented how the system handles temporal variations of the signal leading to a robust performance. And we evaluated our system in two challenging environments, and the results confirmed that LiPhi outperformed the state-of-the-art crowdsourcing and fingerprinting-based techniques. Thank you for your attention.